Hello, thank you for watching this video. So in this video, we'll be doing question 11 of November 2024 question paper mathematics paper 2. And the topic is Euclidean geometry, right? Which is the last question, which is made of similarity and proportionality and your general Euclidean geometry principles. So let's go. They are saying in the diagram, A, B, G, and F lie on the larger circle. A smaller circle is drawn to touch the larger circle internally at A. EA is a common tangent to both circles. EBCF is a tangent to the smaller circle at C. AC is reduced to G. AF cuts the smaller circle at D. AB, CD, and GF are drawn. So, with this situation here, they are saying A, B, G, and F, they lie on the circumference of the larger circle, right? They went on to say that the smaller circle is drawn, so here's the smaller circle here, is drawn so that it intersects the larger circle at A over there. So they are intersecting at A, or they are touching at A. They are saying EA is a common tangent to both circles. So you can see EA here, here's EA, EA is a tangent to both circles. So I'll use a red ink just to show the tangent. So I'll make it wavy. This is a tangent, right, to both circles here at A. So EA over here is the tangent to this larger circle and the smaller circle. So it's tangent to both of them. Fine. What else? They are saying now, they went on to say that EBCF is a tangent to the smaller circle at C. So you have EBCF. This is a tangent, right, as well. It's a tangent to this smaller circle here at C. So let's give this tangent a wavy line as well so that we can clearly see the tangents. Here's a tangent over here. So it is a tangent to this smaller circle at C. So it touches the circle at C, and EA touches both circles at A. They went on to say that AC is reduced to G. So where is AC? Here is AC here. It is extended to go to G over there. They went on to say that AF cuts the smaller circle at D. Where is AF? Here is your AF. Is a chord on the larger circle and touch the smaller circle at D, or cuts the smaller circle at D. They went on to say that A, B, C, D, and GF are drawn. All the other lines are drawn as well. Fine. 11.1, they are saying if angle A between EA, or formed by EA and AG, is X, determine with reason 4 other angles that are equal to X. So we are doing 11.1 now, right? At 11.1, we are given that angle A, right, is equal to X. Angle A is formed by EA and AG. Where is EA? EA is this one. Where is AG? AG is that. A is the angle between the line EA and AG. So the EA is this line here and AG is that line over there. Which is your angle X, angle A is this one over here. So they are saying that this angle here is angle X. The entire angle from here to there is angle X. Which means your A1 and your A2, they both form X. Right? No problem. So they are saying now, determine with reasons 4 other angles that are equal to X. So they want us to find all the angles that are equal to X. Actually 4 more angles that are equal to X. How do we do that? Fine. If AE is a tangent, right? Look at AG over here. AG is a chord. You have a tangent, you have a chord. AC is also a tangent to this smaller circle. AG is a tangent, is a chord of the larger circle. So we're going to apply the Tan-Chord theorem. So what does it say? It says that if you have a circle here, right? Here's a circle, and let's say you have a chord somewhere here. Here's a chord. They're saying if you have if there is a tangent to a circle such that the point of contact of your tangent intersects with your chord, then the angle between the tangent and the chord will be equal to the angle that the chord subtends in the other segment. So this angle over here is equal to that angle over there. And the angle between your tangent and your chord is equal to the angle that this chord subtends on the other side, which is, if you're saying this angle is this, so is that. So that's what the Tan-Chord says. It says the angle between the tangent and the chord is equal to the angle that the chord subtends on the other segment. So in this case, here, you have your tangent, right? And you have your chord there. They're intersecting. And the angle between them is this one over here. So the angle between the tangent and the chord will be equal to the angle that your chord subtends on the other segment. In a similar way, you have your tangent and you have your chord here. The angle between the tangent and this chord is equal to the angle that this chord subtends in the other segment. That's your Tan-Chord theorem. That is your Tan-Chord theorem. So we can apply it here as well. So, look, EA is our tangent, and maybe AC is our chord. So which means this angle X here, which is the angle between our tangent and the chord, which is X, will be equal to the angle that is subtended by this chord on the other segment. Which means, look now, if you have a look at this, the angle X is between the tangent EA and the chord AC. But you can see your AC subtend D1, which means the angle between the tangent and the chord, which is X, is equal to the D1 because angle D1 is subtended by that chord in the other segment. So, in simple terms, we can say D1 is equal to what? Is equal to this angle here, which is EAG, which is X. Why? This is the Tan-Chord, because the angle between the tangent and the chord is equal to the angle that the chord subtends on the other segment. So, in this case, we'll say this is Tan-Chord, which is we have our tangent, which is what? EA, and chord. What is our chord? Our chord is AC. So, we know that this angle D1 here is equal to X over there. That's the first one. This is the first angle, because we want 4 of those angles that are equal to X. So this is angle number 1. Fine. In a similar way, this is your chord, tangent, right? And this is the chord now of the latter circle. AG is the chord of the latter circle, which is the angle between the tangent and this chord will be equal to the angle that this chord subtends on the other segment. So if you're saying the angle between your tangent and the chord is X, AG subtend the angle F there, which is F1 and F2. So this angle, this entire angle over here should also be equal to X. This entire angle here is also equal to X. This is X here. So F1, F2 is equal to X. So what we're going to do, we're going to say, okay, angle number 2, which is F1 and F2, or maybe we can say AFG. Let's say AFG, right, is equal to F1 plus angle F2, right? And they're both equal to, this one here, which is EAG, which is X. Why? This is also Tan-Chord. Say tan, which is your tangent. What is your tangent? Our tangent is AE or EA. And our chord is what? Our chord is the entire chord AG. Right? So, we found the second angle to be X over there. Fine. What do we do from here? Look now. Your EBCF is equal to, is a tangent to the smaller circle HC. But look at this angle over here. This angle is between your tangent EBCF and chord EC. Right? So this angle EBCF, so that the line EBCF is a tangent to the smaller circle HC, which is the angle between this tangent and the chord is equal to the angle that this chord subtends on the other segment. Right? The angle between your tangent and your chord AC is equal to the angle that your chord subtends on the other segment. Which means if this angle is x, so is this one, because they should be equal. So what we're going to say, now for angle 3, we're going to say C1 is equal to D1, which we know D1 already. We found D1 here to be equal to x. Why? This is the Tan-Chord as well. We have a tangent which is EBCF, EBCF, and what? And chord. What is our chord? Our chord is AC, because it's the tangent and chord AC. That's where we are. And we're not done. If you look at C1 and C4, these are vertically opposite angles, right? So this angle over here should be x as well. So you can say for the fourth angle, C1 is equal to angle C1 is equal to angle C4, and that both equal to x, because you know C4 is x already. So C1 is equal to C4, which is x. Why? These are vertically opposite angles. So these are the four angles that are equal to x. This one, and those two. So they're your angles. We're done here. Okay, so now we're doing 11.2. They are saying, prove that AG times AD is equal to AC times AF. So they want us to prove that AG times AD is equal to AC times AF. Fine. So what do you do for this? So let's first identify these sides. Where is AG? AG is this entire side here, right? Where is AD? AD is that small side over here, right? Your AC is this small side here, and your AF is on the other side. So all these sides that we are talking about, they are either on this big triangle or this small triangle over here. So all these sides, because your AG is this entire side here, your AD is this small side over here, your AC, the small side over here, and your AF is the entire side. So all these sides that you're talking about here, they are on the big triangle AGF and the small triangle ACD. So here's what I can do. I can just try to draw this triangle separately on the side. And so let's say we draw this triangle like this. We have A, right? We have G, and say we have F here. And then we have this line here, C, the C here, and then there's D here. So I've drawn this triangle here. What else do we know? We know that this angle here is x, this angle over here. And this angle over here is x. That's all we know about this triangle. That's all we know. So if you look at this triangle, it's straightforward. It's easy to see that these two angles are equal. They are both x. So these are your corresponding angles. So you have two lines, right? CD and GF. They both intersect a transversal or a common third line at the same angle, which means these have the same orientation, which means they are parallel. If you have two lines that are intersecting a third line in an identical way, in exact same way, which means those lines themselves have the same orientation, right? So in this case, this angle here is equal to this angle over there. Therefore, these two lines CD and GF, they should be parallel because their corresponding angles are equal. So what do we say? We say, okay, that is D1, right? So we can say, okay, D1 is equal to this angle here. This entire angle is F1 and F2. F1 plus F2, which is your D1, you found it was X, right? and your F1 and F2, they're both is X as well. So they're all equal to X, right? Therefore, we can say that our CD is parallel to GF. Why? Because the corresponding angles are equal. So, if you're not familiar with this session, go to my playlist and find bet action sessions. Bet action sessions, I'm teaching Euclidean geometry from scratch there. Go to my playlist and open bet action sessions. You'll be able to see this. I did explain this in detail. I was teaching it there. Fine. Then, this is CD is parallel to GF, which means this line over here is parallel to that line. So you can say this is parallel to that. So once you get this now, you are back into proportionality theorem, which I did in the previous question, which is question 10. I even proved the proportionality theorem on question 10. And when I was doing proportionality theorem, I said that if you have this condition, which means this is parallel to this, you can say your AC over CG is equal to what? It's equal to AD over DF. And I said, it does not mean this is equal to this in general and this is equal to this in general. Of course, they can be equal, but not all the time. So to reason for this, you say, okay, this is my proportionality theorem. Why? Because my CD is parallel to GF. That is why your proportionality theorem works. So, which means we said our AC over CG is called AD over DF. This is not the only ratio you can use of proportionality theorem. I said in the previous question, as long as you take the ratios of the same parts, then the ratios will always be equal, which is the proportionality theorem works. So if you're taking the ratios of the same parts, the proportionality theorem will always work. For example, in this case, look what you have. You are told on what you have here. You're told about AG. AG is this entire side. AD is just this small part over here. AC is this small part. And your AF is the larger part. So which means, if you can take the ratio of the small part over the larger part, it should be the same as that of the small part over the larger part. It doesn't matter the order. You can even say AG over AC. It should be the same as AF over AD, as long as you take the ratios of the same parts. So to do this, we'll say, okay, leave this alone. I won't use this. I was just showing the very common proportionality theorem ratio that we use. So what I'll say AG, which is the entire length, over AC. I'm saying AG because I have AG. I'm saying over AC because I have AC. So AG over AC, which is this part. I'm done with that. Is equal to what? It's equal to AG is this entire side. So take the same part, which is the longer side, which is AF over which is where AF, where AD is the smaller part, which is similar to AC, which is the smaller part, over AC. So to reason this, we're saying this is our proportionality theorem, because our CD again is parallel to GF. Right? Then from here we just cross multiply. That's what we're going to do. We're going to clean the side and then we'll cross multiply. So cross multiply A times G, AG times AC. So we will have AG times it can't be AC. So AG over AC is equal to AF over AD. So there should be AD over here. Alright? Fine. Then now we just cross multiply AG times AD. So AG times AD is equal to AF times AC. So we have AC times AF, which is what they wanted to prove to begin with. So we're done here. So we're going to move to 11.3. Okay, so I'm done cleaning the board. So now we're going to do 11.3. So 11.3 reads as follows. Prove that triangle AGF is similar to triangle ABC. So they want us to show that triangle AGF is similar to triangle ABC. So triangle ABF is AGF, and ABC. So that they want us to show that these two triangles are similar. So what does it mean for two triangles? What does it mean for two triangles to be similar? So let's say we have triangle. Let's say it's A, B, C here. And another triangle here. Let's say it's D, E, F. What does it mean for these two triangles to be similar? So, to be similar, you can say they are scale division of each other, right? They are scale division of each other. If you look at them, they look like it's the same triangle, but one is bigger. That's what it really means. One may be bigger than the other. Of course, they can be the same sides, because even if they are congruent, which means they are identical, they are still similar, but they are scale division of each other. So which means if now they are congruent, the scale ratio is 1. But maybe this one is 3 times bigger than that one. So that's what the scaling means. Right? So if you have maybe, let's say this is B. So this will be small letter B here. This is C, this will be small letter C. A, this is small letter A. D, this will be small letter D. F, this will be small letter F. E, this will be small letter E. No problem. So this one is smaller and this one is bigger. So if you're saying these two triangles are similar, this one is a smaller version of this one, or this one is a bigger version of that one. Which means to move from triangle ABC to go to triangle DEF, we have to multiply each of these by a certain factor so that it is this size. It is this size. Which means, let's say it was A, B, and C. And I want to transform it into this by multiplying this triangle of ours by a K, which is a real number. We're multiplying this one by a non-zero real number to be this. Actually, non-zero positive real number, so that it becomes this. So, if I multiply, so if I'm saying triangle ABC is similar to triangle DEF. That's what I'm saying now. I'm saying triangle ABC is similar to triangle DEF. What does this mean? It means that angle A is equal to angle D, which is this angle over here is the same as that angle over there. Angle B is the same as angle E, which is this angle over here is the same as the angle over there. And angle C is equal to angle F, which is this angle over here is the same as that angle over there. So the order in which you write these things you should be very careful about. So if you're saying triangle ABC is similar to triangle DEF, you are saying that this angle is D in that triangle, B is E on the second triangle, and C is F on the second triangle. That's what you're saying. So the order is important in which you write these things. So if you're saying this angle here, this triangle here is similar to this, which is in this order, like your A is your D, your B is your E, and your C is your F. That's why I say star, star, 0, 0, square, square, or right angle, right angle. So that you know that this angle is equal to this, and this one is equal to that, and this is equal to that. In a similar way, so I'm just explaining the similarity part. In the same way I said that your angle A is equal to your angle D, which I've shown. Your angle B is equal to your angle E, which I've shown as well. And your angle C is equal to your angle F, which I've shown as well. So these are things that I've shown. You should also know that you are saying now, if you're saying in that case, your AB, this side AB of yours, corresponds to DE. They are not equal. But you're saying your AB on the other triangle will be represented by your DE. And your BC, which is this length here, will be represented by EF on the scaled triangle. And your AC, which is your AC, will be your DE, will be your DF on the other triangle. So if you multiply these sides by K, they form this triangle, which means if you multiply C, you'll get F, because you can see AB, DE, which is AB, DE. So which means your F will be equal to KC, because which is your C multiplied by K, whatever the factor that you are transforming with. And your B, your E is equal to KB, and your BC, which is represented by your EF, is equal to KA. That's what it means to be similar, which means the angles are equal and these triangles are scale division of each other. And if they are scale division of each other, what does it mean in mathematical form? Which means if you take the ratio of maybe, let's say you say your AB, which is AB over there, and you divide it by what? And you divide it by your DE, right? It's going to be equal to what? Your AB is C over your ED or your DE, which is KC. So your C and C go away. It's equal to 1 over K. In a similar way, if you take your AC there, your AC corresponds with your what? With your DF, which means it's your B over your E. Your E is equal to KB, which is equal to this and that go away. It's 1 over K. You can do the same thing for this as well. If you say your BC all over your EF is equal to your BC, which is A, over your EF, which is D, which is your A over D. Your D is equal to KA over here. So this and that go away. It's 1 over K. So if your two triangles are similar, the ratio of the corresponding sides are equal. The ratios of the corresponding sides are equal, which means, in simple terms, look at this, they're all equal to 1 over K, which means all these ratios should be the same, which is your AB over DE is equal to this. And you need to be consistent, which is, if you're saying the ratio of this triangle over this one, you should do that in all of them, which is this over this, this over this, this over that. And not say this over this is equal to this over that. No. Now you're switching things around. Be consistent. If you're dividing the smaller triangle, divide your smaller triangle throughout. So in simple terms, if you're saying they're similar, I've shown this, which means the corresponding ratios are equal. Which means I'm going to say your AB over your DE is equal to your AC over your DF, which is equal to BC over your EF. So your AB over DE is equal to your AC over DF, which is equal to BC over EF. Even you can swap the ratios around. You can say this over this, equal to this over this, equal to this over that. That's what it means to be similar, which means the corresponding angles are equal and the ratio of the corresponding sides are also equal. So if you want to prove that two triangles are similar, prove this condition or prove this condition. In a similar case, in a case where you are using the angles to prove that the sides, the triangles are similar, you don't have to prove each one. You don't have to prove all this, and that. If you manage to prove that two angles in these two triangles are equal, it will be enough, because it's obvious that that angle is the same, because if these two are adding up to 8 and these two are adding up to 80, right? Which is this angle and that angle will be 100 in both of them. So just proving two angles will be enough to say that these two triangles are similar by angles or similar by corresponding ratios. So let's come back to this. So they're saying we must prove that triangle AGF is similar to triangle ABC. So that's an AGF is similar to triangle ABC. That's the angle A of this triangle Sorry, this is the bigger triangle. That's an angle A of this triangle, which is A3. It's called angle A of the smaller triangle, which is that's like these two angles are equal. That's an angle G of this triangle. It's called angle B of this triangle, which is these two angles are equal. Angle F of the bigger triangle is called angle C of the smaller triangle, and you can see them, they are both equal to x. So you can see those ones are already equal to x. If you can show one more triangle, if you can show one more angle that is equal between the two, you'll be done. In a similar way, which is your AG over AB, which is your AG over your AB, is equal to GF over BC. It's equal to GF, which is this GF over BC, which is equal to AF over AC, which is equal to AF over AC. So that's what it means. But because we don't have anything about length here, so the safe way to try to prove this, or what I think makes sense, the logical way to use to prove this, let's try to use angles, because at least we have something about angles. No problem. So what do? We're told that this is a tangent, right? So we want something about this angle. So we're told that this is a tangent. So look at this angle over here. This angle over here. This angle A1 is between a tangent and the chord AB, right? So you know the Tan-Chord, I did explain it, that the angle between the tangent and the chord is equal to the angle that the chord subtends in the other segment. So which means the angle between the tangent and this chord is equal to the angle that this chord subtends on the other side, which is this angle A1 is equal to F1 over there. The angle A1 is equal to F1 over there. So let's let A1, let's say, let your angle A1 be equal to Y. So let's make this angle Y over here. So if this angle is equal to Y, the angle subtended by B on the other side should also be equal to Y. Right? So we can try to find A2, because we know that A1 plus A2, if you add these to A1 and A2, they make X. So your A1 plus A2, they will give us X, right? But you know A1 is Y, so Y plus A2 is equal to X. Therefore, your A2 is equal to X minus Y. So we get that our A2, this angle here, is X minus Y. That is our A2. But look over there. Look here. You can be able to find F2. Because you know F1 plus F2, they give you X, but you know F1. F1 is Y. Is Y, right? But we haven't written it here. So what we need to do, let's say, we said this angle between the tangent and the chord is equal to the angle that this chord is subtended on the other segment. So let's first start with F1. You can say, okay, F1 is equal to what? F1 is equal to A1. This, and they're both equal to Y. So this is our Tan-Chord. Our tangent is EA, right? And our chord is what? Our chord is AB. Our tangent is EA, our chord is AB. So the angle between the tangent and the chord is called the angle that this chord is obtained on the other side. This is what this means. Fine. So what do we do from here? So what we will do is say, okay, we can find F2, because we said F1, if we add F1 and F2, if we add F1 and F2, they give us X, but we know what F1 is. So we can say F1 plus F2, they will give us X, which is this angle here. We found this. But we know F1 is equal to Y. So Y plus F2 is equal to Y, is equal to X. Which means that your F2 is equal to X minus Y. So, which means this angle over here is X minus Y. This angle over here. The smaller angle F2 is X minus Y. Look this angle. So, you see, you have alternate angles here. So this angle is equal to C3, this angle over here. Look. These are alternate angles on parallel line. This line is parallel to this one. So these are alternate angles. So this angle over here, this angle over here is x minus y. This angle, C3, is x minus y. And EBCF is a tangent. So the angle between the tangent and the chord is equal to the angle of this chord subtended on the other segment. This is the Tan-Chord. This EBCF, this line over here, is a tangent. So the angle between the tangent and your chord is equal to the angle that this chord subtended on the other side. So which means this A3 here is x minus y as well. It's equal to this. So what I'm going to say, okay, C3, which is this angle over here, is equal to F2. And they're both equal to x minus y. Why? These are alternate angles, right? On parallel lines, because your CD is parallel to GF. We proved this in the previous question, that these two are parallel. So, on top of that now, we can say this angle now is equal to that angle because this is a tangent and this is a chord. So the angle between the tangent and the chord is equal to the angle that this chord is subtended on the other side. So we can say now our A3 is equal to C3, and they're both equal to x minus y. This is a Tan-Chord. Our tangent is EBCF. And our chord is what? Our chord is CD. Right? No problem. So let's look at these two triangles again. Angle, we said that if they are similar, angle A is equal to this, angle G is equal to B, angle F is equal to C. And the corresponding ratios are equal, the same way I explained them. Now look at angle A for AGF. Angle A for AGF is x minus y. Look at angle A for ABC, it's also x minus y. Look at G is blank, B is blank. C, F is equal to x, as you can see here, and C is equal to x. So at least you have two angles that are equal between two triangles. So those two triangles are equal. Actually, they're not equal. They are similar. So now that we have shown that two angles of two triangles are equal, you have two triangles that have two equal angles. It is safe to say that those two triangles are similar. Why? Because if two angles are identical in both of them, the other one will also be the same. So in that case now, to prove what they want us to say, now let's come and prove this. We'll say in triangle AGF and triangle ABC, right? What are we going to do? Triangle AGF and ABC, what are we going to do? We're going to say angle A here on this triangle is A3. Angle A3 is equal to angle A2. And they are both equal to x minus y. We've shown this thing above. Right? And we're going to say that angle F, which is F1 and F2. So we're going to say F1 plus F2 in both triangles is equal to what? Is equal to angle C. Right? Equal to angle C1. And they're both equal to x. We have shown this thing. Where? On 11.1. Therefore, these two triangles are similar because all the corresponding angles are equal. We don't have to prove that these two are equal as well because it's obvious. It is obvious because if this angle is equal to this angle, so if this angle is equal to this angle and this angle is equal to this angle, so this angle will be 180 minus the sum of these in both of them. So in that case, we'll say now, therefore, triangle AGF is similar to triangle ABC by what? By angles. Angle. So all the corresponding angles are equal. Even though I've shown two, I don't have to show all three of them. If two are equal, then it's safe to say all of them are equal. So this is where I'm going to stop. I've shown that This triangle is similar to this one. This triangle, ABC, is similar to AGF. And I'm done here. I'm going to clean my board again, and I'm going to do the last question, which is 11.4, which is not very fun. Okay, so now we're doing 11.4. At 11.1, we're finding the values of x in this diagram, as I've seen here. 11.2, we proved this. 11.3, we proved this similarity. Now, at 11.4, they're saying prove that g squared is equal to the product of BC, FC, and AC all over 18. So this is what they wanted to prove at 11.4. So, these questions, I don't think they're very nice to do, because they're very challenging. So, what you should be doing, and there's not even a straightforward way of doing this, or at least that I know of. All I know about doing this kind of question is trying to use what I have to do whatever that they want me to do. So, this is what we're trying to prove. So what we need to do, let's first identify these sides here. GF, what is GF? GF is this side over here. So I'll say GF, GF. I'll put in a circle like this so that we can be able to see it. Then there's BC. Where is BC? BC is this side over here. So we have BC. Right. What else? We have FC. Where is FC? FC is this length over here. So let's say FC. There we go. So this length over here. Then we have AF. AF is that entire length there. So I'm going to put it exactly here on this corner so that it represents the entire thing. I don't want to put it here so that it looks like it's just this, or down here, or just that. So it's AF, so I'll put it exactly on the breakage. AF. So exactly at the corner of that. Okay. So it's the entire side. Then there's AD. AD is just a small part. I'll say AD over here. So these are the sides that we want to have. So these sides, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 are the sides that we need to do this. Right? No problem. So what do we do? So we see that FGF again is on this triangle, which is this triangle here, right? On this bigger triangle. Phi, BC. So this bigger triangle. So we can say BC and your A and your GF. BC and your GF, those are corresponding sides of these similar triangles, right? Okay. FC, the FC is this length over here. FC is this length over here. What does it correspond to? FC, I can't say it corresponds to anything for now. I can't say it corresponds to anything. Unless, because if I can say I take this side and say it's this one. If I want to say this side is this one over here, I would have to prove that these two triangles are similar first. Because, look, FG can be like your BC of some sort. It's not even that. Yeah, it is on the bigger triangle, actually. On the bigger triangle, it is that. But on the smaller triangle, it's something different. So, I want to look at different triangles now. Look. In triangle, let's say ABC. And triangle FGC. Let's look at this triangle. A, B, C, and FGC. Look, if you look at this triangle, angle A is x minus y. Angle F is also x minus y in the triangle. Right? Look at angle C, it's called x. And angle C here is equal to x as well. So these two triangles are similar. So this triangle is similar to this one. And it looks like this one is similar to this one, which is all three triangles are similar. So what you should do, we'll say, what do we say? We say our angle A2 is equal to x minus y, which is equal to F2. We proved this thing before. Proved above. We've shown this above. Look, at angle x, which is angle C1, is equal to angle C4, and they're both equal to x. We proved this thing again, and we can say these are also vertical opposite angles. This was our result 11.1. So these two triangles are similar. We can say that therefore triangle ABC is similar to triangle FGC. By angles, all angles are equal. All the corresponding angles are equal. Fine. Now let's go and have a look at what I was talking about. So if we look at these two triangles now. So let's say in triangle ABC and triangle FGC, the triangles that I think are similar at least, we can say that we can try to talk about these two sides. FC, we can say our FC over FC, you're moving from x minus y towards the x side. X from x minus y to x side, which is from A to C, over AC is equal to what? Is equal to FG, right? FG over, what is the representative of FG? We move from x minus y to nothing, which is x minus y to nothing, which is, this is AB. So what am I trying to do? I'm trying to find some ratio that will contain these things that I have here. So what did I say? I said FC, which is what I have here. Because I said if two triangles are similar and you take the ratio of the corresponding sides, they should be equal. So we said we prove that this one and this one are similar, which is if I say my FC over my AC should be the same as FG over my AB. So my reason for that, I'll say these are corresponding ratios of similar triangles. These are corresponding ratios of similar triangles, right? FC, yes, I do have FC here. AC, do we have AC? No, there's no AC. So let's put a star on AC so that we know these have to go. FG, here we do have FG. AB, we don't have AB. So AB also needs to go at some point. The AB needs to go. Fine. So what can we do from here? Maybe we can just cross multiply the way we did here. Let's just cross multiply the way we did. So if we cross multiply these two, we'll have FC times AB, right? Your AB have a star, which means we don't want this on our, we don't have the one that has a star. And then we say is equal to FG times our AC, right? And our AC have a star because it have to go. So maybe we can say this is our equation 1. I don't know. Let's say this is equation 1. Fine. What are we doing on the second one? We said this, we proved that this was similar to this. That's what we did there. But we know that this is also similar to the big triangle over here. Right? Which means if I look at the bigger triangle now, if I say B, if I take my BC, BC corresponds to GF, and AB here corresponds to AG over there. Right? Yes. So if I can say my BC, let's say BC over the BC, which is this length over here, or let me be clear about triangles. In triangle, ABC and triangle what? ABC and triangle AGF AGF. Right? So we did prove on the previous question here that these two triangles are similar. So if I say my BC over here, which is BC over GF, which is this what you have there, over GF, it should be equal to what? It should be the same as AG, or sorry, AB, right? AB over AG, which is over that length over there, over AG. So, what I've done, I've said my BC, this length over here, divided by the corresponding length, which is the same part on the other triangle, is equal to what? Is equal to AB over AG. So, your BC, do I have BC here? Yes, I do have BC. BC is fine. GF, yes, I do have GF. AB, I don't have AB here. So, I'll put a star on this AB. AG, there's no AG here. I'll put a star on this AG as well. I'll put a star on this AG as well. So what do I do? What I'll do here, I will solve for AB. And this AB of mine, I'll put it back here. Right? I'll solve for AB and take this AB and substitute it there. That's what I'm thinking of doing at this very moment. So, let's solve for AB. Cross multiply there. You'll get that your AB times GF is equal to AB times GF equal to BC times AG. So remember that AG have a star and the AB have a star. The ones that have a star are the ones that are not part of this formula, so they have to go, right? They have to go at the end. So what do we do? So, what do we do? Now we say we're going to solve for AB, divide by GF both sides. You get that your AB is equal to BC times AG all over GF. So, remember, your AB have a star and your AG have a star. So, let's say this is equation number 2. So, let's substitute equation number 2 in equation number 1. So, your AB, you put it there. So what you will have FC times AB. AB is that entire thing. It's just FC times AB. AB is that entire thing. So it's BC times AG all over GF, right? Is equal to FG times AC. So let's remember to put back the stars. So AG had a star and AC had a star. So I'll just get rid of this by multiplying throughout by AF by multiplying throughout by FG. So you can see that these things are multiplying each other, right? So if things are multiplying each other, you can think of them as one term. So this FG will not multiply here and multiply there and multiply there, because those things are multiplying each other, so it's just one term. So GF is dividing all of them essentially. So let's just cross multiply. So maybe this is all over 1, right? This times the top, so you have FC times your BC times your AG is equal to your GF. GF times GF is GF squared, right? Because there's 2 of them. So it's GF squared. So there was a 1 here times AC, right? So remember that this have a star and this have a star. So these 2 things that have a star, remember that they were here. So you had, or not you had to prove at level, you had this and your AC, which is this. Your AF and your AD, they are part of this formula because there is your AF, there is your AD. So these you don't have to put stars on them. So what you need to do now, if you were able to take, let's say you divide by AC both sides and take this to the other side. So let's do this. In this case, what do? we divide by FC times BC, né? FC times BC. You want this to come to this side. You want this to come to the side. So divide by AC this side as well. Divide by AC. We're not leaving the star. So what will happen? This and this will go, this and this will go, this and that will go. So what I'm left with, you're left with AG over AC. Left with AG over AC is equal to GF squared over FC times BC. Yeah, just these two. So of course, these two have a star. So you have a ratio of AG to F to AC. This ratio, you can find it here. You can find it here. So let me just clean this board here. So do the same thing here. Divide by AC, divide by AC, divide by AD. So this AD can go, divide by AD. So this and this go away, this and that go away. So what you're left with here, you're left with AG over AD. AG over AC is equal to AF over AD. So of course, this has a star and this has a star. So your AG over AC is equal to AG over AC is equal to AF over AD. So this star is equal to this. So which is this thing is equal to that thing. So take this equation of yours, this, and equate it to that, which is equate the right hand side. So the left hand sides are exactly the same, just equate the right hand sides. So which means your AF over your AD, right, is equal to your GF squared over your FC times BC. Then you want your GF squared, cross multiply. So if you cross multiply this thing, it will be this times just that. I'll not cross multiply, I'll multiply by this times by FC and BC this side, times by FC, BC on the other side. So what you have, this and that will go away. So you get that your GF squared is equal to your FC times your BC times your AF all over your AD. I believe this is what they want us to find. Yeah, I believe that is what they wanted us to prove. And BC, FC, AF, AD, yes, it is the one. And there's no formula for this, it's just you trying to relate things on what you're given. And I hope it does make sense to you as it does to me. And I'm done with this question. I'm going to do another paper now. Thank you for watching. Cheers.